Okay, so what are some of the other technologies that we've used? Pump and treat I talked about was kind of our starting technology, but there's a variety of other technologies, and certainly some that have come about and become more commonly used in the last decade or so. Air sparging is an option that we have for remediating groundwater in situ. And that's one where the air is injected into the groundwater, and then as it rises up through the aquifer, it strips off the solvent. So it's essentially the equivalent of an air stripper, but it takes place in the ground. And it worked pretty well. One of the drawbacks of air sparging is that as the air bubbles are moving up through the aquifer being like the sandy, silty clay environment, but as those air bubbles are moving up through the aquifer, they can set up channels. And so you can get some really nice treatment within those channels and then have virtually no treatment on the outside of that. So you get some homogeneity problems. Multi-phase extraction is another one that we use. It's a high vacuum system that we can use to extract multiple phases. So either air and soil, or soil gas and groundwater, or perhaps groundwater and free product. We might commonly use this in sites where we have oil, free product oil or gasoline, since that floats. TCE is denser than water, so it has a tendency to flow through the water column and continue downward as far as it can go until it hits an impermeable layer. Another option that we don't use too much because it's really expensive and very energy intensive is in-situ thermal. So in-situ thermal is one where we use electrodes or heaters that are attached to a power supply that actually heat up the subsurface and volatilize the chemicals while they're still underground. So the chemicals will volatilize, and then we would use a soil vapor extraction system to extract the vapors and treat them. In-situ thermal can work well when you have a very specific small area that's a source zone that you want to treat. But you're not going to use that for large plumes because it's just terrifically energy intensive and very expensive. So that's another thing that we're working on, particularly over the last couple of years. We've really worked a little bit harder, actually I would say a lot harder, to make our remedies greener. So as we continue to look at our remedies, what are ways that we can optimize the system to use less energy, to use less water, to have people traveling back and forth to the site less. And I think, did you want to do the raffle now?
No.
Okay. No? Yes?
We can wait.
Okay. We'll wait. I'll break pretty soon, but apparently people are waiting for the Kepler's gift card. Everybody wants to win that, right? Okay. Another groundwater remedy that we'll use is in-situ chemical oxidation. And this is another in-situ remedy, so it takes place completely underground, where oxidants are just injected into the ground, and then they oxidize the contaminants, literally break apart the bonds, turn them into harmless chemicals. So a couple of oxidants that work well are hydrogen peroxide, catalyzed hydrogen peroxide, which is called Benton's reagent, potassium permanganate, sodium persulfate, sodium permanganate. There's a variety of different oxidants that work well. Potassium permanganate works pretty well, and it's less aggressive than hydrogen peroxide. Hydrogen peroxide tends to be really aggressive, so we're going to be a little bit cautious about using that sometimes in residential areas. But potassium permanganate is an oxidant that works well, and hydrogen peroxide works well at some sites as well. So then this is another in-situ remedy. Now, with all these in-situ remedies, one of the most challenging things we have here in the Silicon Valley, and particularly in the South Bay, these Bay margin sites, is getting the products, the materials into the subsurface. So the Bay margin here, because the water level in the Bay has risen and fallen over the course of hundreds of thousands of years, what's underground, beneath us, is interbedded sand, silt, and clays. So you have these layers of clay, which is very, very fine particles. You have layers of silt, you have layers of sand, and they're all intermixed with each other. And so the contaminants like TCE get into the clay, they get sorbed into the clay. They literally adsorb into the clay, and then they just remain there until they sorb back out. And because TCE is relatively insoluble, it just takes decades for this stuff to come back out of the clay. That's what makes these sites so problematic. So with the oxidants and some of the other in-situ techniques that we're going to be looking at, we have similar problems. We can put in an injection well, and we can inject this material into the subsurface, And we usually, use a little bit of pressure, but not so much that it's going to blow out our monitoring well or our injection well. But getting it actually into the subsurface, getting it very far out into the subsurface is really pretty problematic in this environment. And it's another one of the challenges that makes cleaning up groundwater here really, really difficult. So another in-situ remedy that we use is bioremediation, and then associated with that, bioaugmentation. So bioremediation occurs in anaerobic environments. So these are low oxygen environments, and that's how TCE and some of these other chlorinated solvents are degraded. So the subsurface is very low in oxygen. For all you biologists, it's typically less than 1 milligram per liter. So it's almost difficult to measure on the field instruments that we have, but it's very, very low oxygen environments. And so there are microbes, there's bacteria that occur naturally in these environments that actually eat up the contaminants. And so these bacteria were discovered because they occurred at these sites, and we could see that the contaminants were breaking down. There's a very identifiable breakdown product for these contaminants. PCE breaks down to TCE, which breaks down to cis-1,2-DCE, which breaks down to vinyl chloride, ethene, ethane, and eventually to carbon dioxide and water. And so at sites where we were seeing this breakdown product, particularly cis-1,2-DCE, which is the next product down from TCE, we could see that, okay, there's something going on here. These natural bacteria, these microbes that are in the subsurface, are breaking down these contaminants. Well, what bioremediation does, or enhanced bioremediation does, is we simply assist that naturally occurring process. So we basically feed the microorganisms. We give them nutrients, such as cheese whey molasses, vegetable oil, sodium lactate, and what that does is it boosts the microorganism population in the subsurface and then makes them better able to eat up the TCE and other contaminants. So bioremediation works pretty well, and it's a technology that's really come into force over the last decade or so. We're using this at many, many sites. And then bioaugmentation would be where we inject additional dehalogenating bacteria, basically just to jumpstart the process. And these are naturally occurring. They're not, genetically engineered or anything like that. But with the bioaugmentation, one of the problems there is that if we're injecting the microbes into a subsurface that's too aerobic, they're just going to die off. These microorganisms really have kind of a narrow window that they like to live in. So it's got to be an anaerobic subsurface environment. The pH has to be right. Sulfate concentrations can't be too high. So bioaugmentation can work, but it's in some cases just a wasted effort because the subsurface just is not adequate for bioremediation to take place. So for the most part, what we do is just inject the nutrients to assist the naturally occurring microorganisms that are already there in the subsurface. And you'll notice that these are all food-grade products, the cheese whey, molasses, vegetable oil, sodium lactate. There also are proprietary solutions that also work quite well and can actually last longer in the subsurface that have the same effect that feed the microorganisms. But we found that communities typically like to see food-grade products. So, when you talk about, oh, we're injecting these things into the subsurface, and, it's sort of people are, well, what? Bugs? Microorganisms? No. These are all naturally occurring microorganisms, and so by feeding them the food-grade substances, the carbohydrates, we basically feed them and allow them to do the work on the chlorinated solvents. Okay, this is another example from Alana's site. And so these were some test wells that they put in for their pilot test of in-situ bioremediation. And you can see from the parking lot here, these are actually the test points. And you can see these are very close together. They're about 10 feet apart. Is that right?
Yeah, or less, yeah.
It's about that. Really, really tight spacing. And it's again, because I talked about the subsurface being very, very tight. So by having these injection wells, you can see there's an injection point right here. So you simply have a truck. Where's my arrow? There it is. And so they're injecting, in this case, at this site, you guys were using emulsified vegetable oil. Okay, so this is looking down into the tank. This picture, I'm losing my arrow here, is looking down into the emulsified vegetable oil. So it's emulsified, it's basically just vegetable oil, but it's emulsified so that it's a mixture. It's basically just a froth. Because otherwise, if you were just going to use vegetable oil, it would be like your salad dressing. Salad dressing, vinaigrette or something, you have to shake it up before you use it. It's the same thing here. So you inject it with these injection points, And these are going to be very closely spaced because even by pressurizing the nutrients as we inject them into the subsurface, it's still very hard to get them out into the formation because the silts and clays are so tight. Okay, so another technology that's in use now at more than 100 Superfund sites across the country are permeable reactive barriers. And these are walls that are built into the subsurface that are permeable, as the name implies. And one of the most popular and most effective of these types of walls is called a zero-valent iron wall. And so this is an abiotic reaction. The contaminants, the TCE, PCE, other chlorinated solvents, come in on the up-gradient side, and they're actually abiotically degraded within the wall, which is really only, a foot to a couple of feet thick. And then down gradient, you basically get clean water. So it's kind of a silver bullet, and it actually works pretty well. There's some long-term challenges with this. When these walls are installed, they basically dig a big trench, and then they backfill it with zero-valent iron, which is a great media to use because it's pretty cheap, and it works quite well. But then after a period of years to perhaps decades, the original permeability that you had in that wall, obviously you want your groundwater to go through the wall. You don't want it to go around the wall, right? So these walls are designed so that they are more permeable than the surrounding environment because you want to drive the groundwater to the wall. In some ways, sometimes we'll put in funnel and gate systems where you actually have impermeable walls on the outside and then your permeable wall on the inside to really force the groundwater to go through the wall. But then after a period of many years, you get precipitation, you get salts that get embedded in the wall, and so your permeability is reduced. And then the risk there is that your contaminated groundwater is simply going to go underneath the wall or around the wall. And with installing these systems, you also need to have them keyed into a base layer. So this diagram doesn't really show it, but the base of your wall, you definitely want it tied into a relatively impermeable layer, a clay layer or something like that, because otherwise, with time, your groundwater can just go underneath the wall, if that's an option. But where they're used, they typically work quite well. And so with some of the new heavy equipment technology, you can actually install these to as deep as 100 feet. Most of them are more in the depth of 30 or 40 feet typically. But there are some ways that you can dig a deeper trench and then you backfill it with actually a biodegradable slurry. Then you put in your zero-valent iron, and then with time, the biodegradable slurry degrades, and then you're left with the zero-valent iron. So that's one way of putting in a deeper wall where you're not, so that you don't have the sides of your wall collapsing. And so one of the latest things on the zero-valent iron walls is using nanoscale zero-valent iron. And the advantage with that is that nanoscale are really teeny tiny particles. They're, I guess the technical definition is 1 to 100 nanometers. It's about that. They're really, really small. And so by using nanoscale zero-valent iron, you increase your surface area. So your groundwater has more contact with the zero-valent iron than it would with just typical granular iron. Okay, and then the last technology is one that we use pretty much at all our sites, and it could be used as a standalone remedy, or it could be used more commonly in conjunction with an active remedy. And so this is called monitored natural attenuation. And this is used at sites that aren't very contaminated, that the groundwater contaminant concentrations are so low they can really degrade on their own, or it's used as a companion remedy to an active remedy. So you might have a permeable reaction wall combined with down gradient monitored natural attenuation. Or you could have bioremediation near your source zone, and then down gradient you'd have monitored natural attenuation. And so as the name implies, the contaminants naturally attenuate. We do monitor them regularly with groundwater monitoring wells. There are a variety of attenuation mechanisms that are allowed. EPA has a preference for this first mechanism, biodegradation, because it means that the contaminants are completely broken down. But we also allow dispersion, dilution, sorption, and volatilization. Those are also considered attenuation mechanisms. And I think I will turn it back over to Alana. Unless we have the raffle?
Oh.
I really want to see who's going to win that gift certificate.
I'll let you take it.
Oh, you get to pick it.
Oh,
You can
sweet.
do it and then read out who our winner is.
Better not be my brother. That would look bad. Oh, no, it's Bob. Carol Wong. Yay!
Thanks a lot.
Thank you.
So Kathy talked about what EPA and the other agencies have been doing to clean up the groundwater. What I'm going to talk about next is what I refer to as a newest exposure pathway.